Welcome back to this course. As we deal with this number theory, we are into the second part of the number theory. And today we are going to consider a few more schemes that are part of this number theory. We will begin with the random numbers and go on to see some parts of the methods of proof as well. So let's start today's lecture here with this thought of pseudo-random numbers. So, well, you know what is a random number, but here is the question: what is a pseudo-random numbers? Well, since computers cannot generate truly random numbers, we try to generate a number that are close enough for a random numbers, which are not truly random, but it's quite close enough. So that's why we call it as a pseudo random numbers. So we try to have an algorithm for random numbers. Let's try to find this simple algorithm. Of course, you can have your own algorithm. There are a lot of algorithms developed to generate random numbers. So here is one of the algorithm that you are going to see. So we are going to choose 4 integers. Let's have a seed value of x0, that is the starting value. Then you have the modulus m, that is the maximum possible values. Then the multiplier a, which lies between 2 and m, and you are going to increment with c, that lies between 0 and m. So there are 4 integers: x0, m, a, and c. With this we can frame the algorithm. We have this form of the random number generator: x sub n plus 1 equals ax sub n plus c mod m. So did you find all those integers there? Yes, you have x, you have c, you have a and m. Well, with this we can try to generate it. So you have this formula there. The formula here is x sub n plus 1 is equals to ax sub n plus c times mod m. So we are going to select x0, which is the starting point, to be 3, and m, which is 9, and a is 7, and c is 4. We know, just recall what it is. C is the incrementer, and you can see a is the multiplier and m is the maximum possible value. Okay, let's try to use this into the formula. For x1, it happens to be that you are trying to use these values. So you know that a is 7 and x0 is there. So when n is 0, that's what happening. x1 equals 7 x0 plus 4, that equals 7 times 3 plus 4, that equals 25 mod 9, that equals 7. So did you get this whole idea, the whole picture? Because we know x0 is 3 initially, so that's why we had this 7 times 3 plus 4, so that gives 25. And then we have this formula, right? After we got 25, you have a formula mod m. So m is 9 and 25 mod 9. So we know that as far as the modulus is concerned, we just take the reminders. So when you divide 25 by 9, the remainder would be 7. So that's what you got here. So now you got what is x0, in fact what is x1. Now you can try to generate what is x2. So to generate x2, you are going to use your x1 there, and again 7 times 7 plus 4, so we have 53 mod 9. Again you get the remainder there. as 8, because you know 45 evenly divides 9 and then 53 does not, and it generates the remainder of 8. So that is your x naught. Then again for generating, that is your x2, x2 is placed here, you generate x3. Then the same thing can be repeated again and again. You are going to generate x3 and put it on to generate x4. You have got x4, try to put it in this form to generate x5, so on and so forth. So you can see you are randomly trying to generate these numbers with this given formula, and it goes on and on. But does it goes on and on forever? Let's see. So you got the sequence generated here, 37861204537861204553. As you see this sequence, did you note that the sequence repeats? Yes, but it selects all possible numbers before doing it. So this is a simple form. You can see here, for example, the repetition happens only after we have 8 digits generated. In fact 9 digits are generated. Then you are trying to generate the same thing again and again. So in fact you can call like 8 digits are generated first, and then you are trying to generate this again and again. It's kind of a repeated one. So the common algorithm people use today for m equals 2 power 31 minus 1, and this one you have to choose 4 billion numbers before it repeats. 4 billion random numbers before it repeats the sequence. So that's kind of quite large numbers, and even you don't really notice that it's going to be the pseudo random. It seems to be a real, truly a random number. Well, let's move on with this Caesar's Cipher. Julius Caesar used this to encrypt messages. What was that? A function f to encrypt a letter is defined as f of p equals p plus 3 mod 26, where p is a letter. So we have 0 for A, 1 for B, and 25 for Z. So what we are going to do is that we are just mapping the digits with that of the English characters A to Z, and then while decrypting this, what we are doing is f inverse of p equals p minus 3 mod 26. Let's see how it is done. So we can simply substitute to obtain the original informations or messages. So let's say you're asked to encrypt this statement, go Cavaliers. So to translate to your numbers, you have g equals 6, y equals 14, etc. You try to just translate. So you have the full sequence here, 6, 14, 2, 0, 21, 0, 1, 1, 8, and so on. You have translated it, just mapping, after mapping the alphabets and numbers. Now apply this Cipher to each numbers, f of 6. So for f of 6, you can say it applies to 9, because we are adding p plus 3. So your original value is 6, you are adding 3 to it, so it produces 9. Then your original value is, for example, for O, it is 14. but now after adding 3 it becomes 17. So now you have another full sequence after encryption, that is 9, 17, 5 to 9, 17, 5, 3, 24, 3, 14, 11, 7, 20 and 21. Well, let's see how we can convert. If you convert these numbers back into letters, for 9 you have J, for 17 you have R. So it's like the full sequence of letter. Originally it was Go Cavaliers to the new sequence of after encryption, the sequence becomes JR space WFDY DOLHUV. It doesn't make any sense as such. Well, that's your decrypted encrypted message, and you can in fact decrypt the same message. So for decryption, what we have to do is just do the reverse process. You have the whole sequence there, and take the sequence and you are going to apply F inverse, that is P minus 3. Just apply for every numbers in this sequence and then convert this into the alphabets. So you get the full sequence as the original one. It sounds simple, but it's quite a useful tool for cryptographies or encryption and decryption. It's a very simple logics that has been used, and you know, who knows that this has been used even before 1000 years. Let's even if you want to try to use it for applying for other purposes, even say for example you want to use it cryptography or simple logics in your programming terms, still you can do it. So Caesar gripper must translate letters by 13 instead of 3. So for example, you can apply some function to decrypt it, like 13 plus 13 is 26. So rot 13 stands for rotate by 13. So this example you can see you have a message and then you can encrypt this message. You are adding 13 to it and then whole thing is quite repeated or rotated and the whole message becomes more complicated. So originally you talk about the earth rot is Luke Skywalker's father, and then you do this function rot 13 or rotate 13 for encrypting the original message. Well, we can stop there with that of this cryptographics, and we will not talk much on that in this lecture. Just for your reference, I was mentioning about how things are taken care of by means of the number theory. A simple logic can be useful to hide messages. Now we are into some of the important topics of these lectures, which is method of proofs or proof methods. So here we have 10 different types of proof methods, and we will focus more on first six methods, and then later on we do have like the remaining 4 methods. But we'll first start with the direct and indirect proof, then we'll talk about Waker's proof, trivial proof, proof by contradiction, proof by case, proof by equivalence, existence proof, uniqueness proof, counter example. So let's see one by one. What is the direct proof? Consider this implication: P implies Q. And with this thought of P implies Q, if P is false, then implication is always true. So thus show that if P is true, then Q is true. So it's kind of a direct proof. Just show that P is true, and then you know that Q is true. So to perform a direct proof, assume that P is true, then show that Q must be true. That is the idea behind the direct proof. So let us see this simple example of a direct proof. And here in this example, let us show that a square of an even number is an even number. So let us rephrase it this way: if n is even, then n square is even, right? So assume that n is even. Thus n equals 2k for some k, a definition of the even numbers. So then n square equals 2k square, that is 4k square, that is n square equals 2k the whole square, that equals 4k square, that equals 2 times 2k square. And you know that as n square is 2 times an integer, n square is thus even. So you can simply refer back to the original definition of direct proof. We have this form here: if n is even, then n square is even. This is like just like P and Q, right? So we are asked to assume that n is even. So we know that, assume that P is true, then show that Q is also true. So we assume that n is even. By this assumption, we showed that n square is even. So that's the main idea behind this direct proof. What is indirect proof? Let us see this again. Consider the same implication like P implies Q. So in this implication, you have this contrapositive: negation of Q implies negation of P. So we know that the contrapositive and implications, their relations, they are kind of logically equivalent. Yes, the implication and contrapositive are logically equivalent. So if the antecedent, the negation of Q, is false, then contrapositive is always true. So that's what we try to say here. That's what we try to prove here in indirect proof, indirectly proving the implication. Thus show that negation of Q is true, then negation of P is true. Let us see, to perform an indirect proof, do a direct proof on contrapositive. So let us consider, if n square is an odd integer, then n is an odd integer. So to prove the contrapositive, because we know that we have to do this approach by means of direct proof initially. So to prove that contrapositive, if n is an even integer, then n square is an even integer. Can you see the relationship again? So if n is an odd integer, which is P, then n is, if n square is an odd integer, then n is an odd integer. This is Q, right? So now I am going to have its contrapositive, which is, if n is an even integer, which is negation of Q, then n square is an even integer, which is the negation of P. Got it? We got the contrapositive. So proof: n equals 2k for some integer k. So this is the basic definition of even numbers. So n square equals 2k the whole square, that equals 4k square, and again that's equals 2 times 2k square, and eventually this proves that since n square is 2 times an integer, it is even. So in fact we use the simple way to show it. So which one to use are you going to use the direct proof or we are going to use the indirect proof? When do you use the direct proof and when do you use the indirect proof? What is there? So if it's not clear for a problem, try direct first, then indirect second. If direct fails, try the other proofs, that is indirect. If indirect fails, again you have other 8 different proofs. We saw that there are 10 different way of proving things. Yeah, you can try other proofs as well. So here is an interesting observation. In fact, it's a theorem, as well as we'll see how things can be proved. So the question given to us here is, a square of any odd integer has the form 8m plus 1 for some integer m. So here we can suppose, you are going to suppose you are talking about a square of any odd integer, and this odd integer has the form 8m plus 1 for some integer m. So since we talk about this odd integer, let's try to assume for odd and then try to prove things in the same way. Since we can say that we have an integer, say for example n is odd, and if n is odd, we try to equate this to that of n odd numbers. So we know that, for example, if you have a number, say for example 4q and 4q plus 2 or even, if that is the case, then we know that n is odd. So n is of the form, we can say 4q plus 1, or you can say 4q plus 3, because n is odd. So with this we will try case by case and try to see how this fits our need. Let us consider the case 1. In the case 1, let us say n equals 4q plus 1 for some integer q. So here we must find an integer m such that n square equals 8m plus 1, because the question is the square of any odd integers has the form 8m plus 1. So that is what I was wondering. So here we are talking about n square is of the form 8m plus 1, and since you know n equals 4q plus 1, can we rightly say that n square equals 4q plus 1 the whole square? Yes, that is by means of substitution, you can clearly see. And now you can try to say how the things can be written, because by definition of square you can write it of this form, and once you try to simplify this, you will have the form 16 square q square plus 8q plus 1. In other words, we can have 8 2q square plus q plus 1. So this is a simple algebra by means of which we can conclude this part. So here again, can I rightly say that m equals 2q square plus q? Yeah, if I can do that, then m is an integer, since 2 and q are integers and sum and product of integers are again the integer. So just by simple substitution method, you can simply write it as n square equals 8m plus 1, where m is an integer. So it's kind of a simple proof for our given example. So let's try another way and see whether we can make it. Say for example, let's say n equals 4q plus 3, and for some integer q, with a similar thought that we had before. So we must find an integer m such that n square equals 8m plus 1. Since we know that n equals 4q plus 3, can we rightly say that n square equals 4q plus 3 the whole square? And with this thought, again we can simplify 4q plus 3 times 4q plus 3 is, and simply try to solve it, 16q square plus 24q plus 9, and again try to simplify it, 4q plus 8 plus 1. You can take 8 outside, so you have 2q square plus 3q plus 1 plus 1. Yeah, just a simplification process. So in fact, again, what we have come up with in this part, it's very similar to the one we have done in other case, right? So in this case, the second case, we used n equals 4q plus 3, and eventually we are trying to solve the same problem here. So we can clearly see that from here m equals 2q square plus 3q plus 1. Then m is an integer. We know that since 1, 2, 3 and q are integers, and again sum and product of the integers are still integers. So just by substituting, you can clearly say that n square equals 8m plus 1, where m is an integer. So both case 1 and case 2, given an odd number, whether of the form 4q plus 1 or 4q plus 3, we can show that n square equals 8m plus 1 for some integer m. It's a simple proof for us to get along. Yes, we have moved a long way from the pseudo-random numbers into a method of proofs. We know what is a direct proof, and we have seen examples of direct proof and indirect proof. Let's talk more about other proofs in the coming lectures. So as we are here in this part of proofs, it's an interesting area where we try to prove things, right? So as you try to prove things, of course the logic also comes into picture. So you will notice it in the coming lecture as we try to prove other methods of proof. Until I see you in the next class, have a nice time and goodbye.